Hi, this is Paul Mickelson, and this is for Education 530 Instructional Methods. This is my micro teaching lesson concerning Module 7, and once again, my name is Paul Mickelson. And what we're going to concentrate on today, what we're going to teach today, is a chemically related equation called the ideal gas law. And I think, what I like about the ideal gas law, what I'm going to express to everybody today, is it's a very interesting equation that comprises elements not only of chemistry, which is what it's founded in, but also earth science, general science, elements of mathematics, physics. It's just something that, when you put it all together, it really encompasses a lot. And really, it's not that difficult an equation to use, but it helps you figure out real elements of everyday life, which we'll talk about in a minute or two when we get into the actual calculation we're going to perform with it. So once again, I'm going to teach a little bit today on something called the ideal gas law. Has anybody ever heard of that? My assistant here, have you ever heard of the ideal gas law yet?
No, I have not, sir.
Okay, thank you. What it really comprises, where its foundations exist, were elements of Avogadro, Boyle, and Charles. And what they did in the early years, before the ideal gas law was put together, with Avogadro, which of course if you're involved in chemistry you're familiar with the Avogadro's number, but with Avogadro's law itself, relates elements of ambient, which is to the amount of a given substance in chemistry terms. We're dealing with volume, and N is the marker for that. Boyle's law related pressure to volume, PV, pressure volume 1 equals pressure volume 2. And then Sir Charles came along. That's not the basketball player. Sir Charles came along and he related volume to temperature, V to T. So I think what we're going to kind of loosely bring up right in the initial part of this lesson is things we want to extract out of this in the end, and we'll talk about more about that when we're done. But we're going to think about and become familiar with the term, how it relates to adiabatic cooling, which is reducing heat through a change in air pressure. We're going to talk about more about that toward the end of the lesson. We also want to think about and become familiar with ambient conditions, which, your surrounding environment. For example, what do you think an ambient temperature would be that you're comfortable with? My assistant, can you think of a comfortable temperature? Room temperature?
65.
Okay, she likes 65. 65 in what units, if you don't mind me asking? 65 Fahrenheit, Celsius?
Fahrenheit.
Units are very important in chemistry. So when we're dealing with equations, units are every bit as important as any element that you'll learn in chemistry. So never forget your units. Okay, my assistant likes 65. Actually, ambient is said to be somewhere in the vicinity of 68 to 75. But like my assistant, I really like it down around 65 Fahrenheit. And we're also going to, toward the end of the lesson, I want you to concentrate on what we're going to talk about, diatomic molecules, and I'm going to refer to two diatomic molecules in my equation when we go over this. And diatomic molecule is just a molecule that can't exist by itself in free nature. If you look at the periodic table, you'll see oxygen, for example, but oxygen exists as O2. Nitrogen, it doesn't exist as nitrogen unless it's bound to something, or if it's by itself, it has to exist as a diatomic molecule, N2. So we'll talk about that, and then part of your homework will be to give 3 or 4 other examples of diatomic molecules. Okay, how are we going to use the ideal gas law today? I've got a simple question here. Well, actually, it may not be that simple, but we'll make it simple. And the question is this. We want to calculate the pressure developed in a bicycle tire when a certain amount of air is pumped in at a certain amount of temperature, okay? So we have some roundabout units here. We'll go with what we're given in the equation. And again, we're going to be using the ideal gas law, which is PV equals nRT. Can we just focus down here? pressure times volume equals quantity of the element or the compound given times a constant times temperature. Now the constant's important because it ties together the units that we're using for this particular equation. And there are several different specialty gas constants that we can use to tie together different units, but we're not going to get into all that. We're just going to use the one we're going to use, and I'll tell you about that in a little bit. Okay, so once again, P equals pressure, V equals volume, N is the quantity. In chemistry terms, that'll be number of moles. We'll figure out number of moles based on the quantity of mass that we're given, constant, and the temperature. So the required units we're going to use for this example in pressure, which is what we're going to find, are atmospheres to begin with, okay? Ultimately, we're going to want to turn that into pressure developed in a bicycle tire, PSI, because you certainly aren't going to go to your service station and say, give me atmospheres in my tire. They're going to laugh you right out of the garage. So we're going to want to convert that. But for the purpose of this equation and the constant we're using, we're going to use atmospheres. Volume is going to be liters. The amount quantity, as I mentioned, number of moles. And our constant is going to be liter, mole, atmospheres, Kelvin. Kelvin is our temperature scale that we're using here today. And again, you can see we're given our temperature in Fahrenheit. So ultimately, before we start this question in this equation, we're going to have to convert this. Make sure you focus in on this here. Thank you, Ash. Over to the proper units, okay? So this is what we're given. 1 atmosphere, and in our equation, we know that 1 atmosphere equals 14.7 psi. This is just roundabout notation for you. We're given, what do you think the pressure that we're given, calculate the pressure developed in an 800 mils, so that would actually be the volume. What is the volume? It's 800 mils, that's what's given. The quantity of the compound we're looking for is air, okay, we're given 4.0 grams of air. And our actual numerical specialty gas constant here in this case is going to be 0.0821. And the temperature that we're given is 104 degrees Fahrenheit. Okay? So now we have to put this into friendly units that we can use for our equation. So we know that we have to go, we got atmospheres, okay? So we're okay with that. Now let's take a look at over here. Can you just come on over here? You can stand up and film me over here. First thing we're going to convert is into the quantity of the compound that we need, the quantity of the element. Okay, so we got 4.0 grams of air, and we need to convert that into moles, which is really, I mean, when we're dealing with a chemistry problem, everything basically has to be converted into moles. So we're given 4.0 grams of air. So what is air? Ash, can you tell me what air is basically? I mean, we're not going to go over all the trace elements. Okay. Air basically is 80% nitrogen, which exists diatomically, N2, and 20% oxygen, which exists diatomically, O2. So from the periodic table, when we look at the atomic weights, we can see that in free nature it exists again diatomically as 14 AMU, which is the weight on the periodic table. Diatomically, we have to multiply that times 2 to come up with 28. That's the weight and mass of nitrogen that we're using in this equation. In oxygen terms, we're dealing with 16, which is the mass of the oxygen in the periodic table. And again, it exists diatomically. 2 times 16 is 32. So as I said, air is 80% N2, 20% O2. So we're taking 80.80, which is, we're taking the decimal form of the 80%, 0.8 times 28, plus 0.2, which is decimal form of 20% times 32. We come up with 29 grams. Now, we have 29 grams of air is equivalent to 1 mole. But in our equation, we said that we have 4.0 grams of air. So using the scientific method, as it's called, in chemistry terms, we're going to take 4.0 grams of air. We're going to convert it to moles by the scientific method. So if you look here, 4.0 grams, 29 grams of air equivalent to 1 mole. The units cancel in grams. We're left with moles. And we come up with basically 4.0 divided by 29, which is 0.14 moles. Now we have a quantity we can work with in the specialty gas equation. I had to throw this in as an afterthought here because I should have shown that we actually have to also convert the volume to liters, and we're given 800 mils. And I think if you go back to your middle school science, or even in this day and age, elementary school science, you'll find that when you have something in milliliters, to convert it to liters, you simply divide it by 1,000. So 800 mils divided by 1,000 gives us 0.80 liters. So now that's what we're going to use as far as the volume goes. So now we have the amount N, the volume, and we have to convert temperature to Kelvin. So we're given our temperature in Fahrenheit. So actually Kelvin is 273.15 plus degrees Celsius. So we have to convert Fahrenheit to Celsius. And I like to get rid of the fractions. I like to use 9C equals 5F minus 160. So we simply input 104 where the F is here. That's your algebra, okay? So we have 9C equals 5 times 104 minus 160. Ultimately, that gives us 40 degrees centigrade, okay? Now, to come up with Kelvin, we just simply add that 40 degrees centigrade, okay, to 273.15. Lo and behold, now we have 313 degrees Kelvin. So now we have all the useful information we need to input into our specialty gas equation, okay? We have the pressure, we actually have the volume in the correct units, the quantity in the correct units, and the temperature. We're solving for pressure, and the R is our constant. So once again, come on down here and take a look. We have for solve PV equals nRT. Again, using algebra, we're going to solve for the P, which is our pressure, and we're going to say P equals nRT over V. And of course, that's your algebra. So inputting our numerical values, first thing we're going to do here is pressure equals N, right, which is the quantity, 0.14 moles, times our specialty gas constant, which is 0.0821 liter atmosphere moles Kelvin, okay? Those are inverses, the moles and the Kelvin, times our temperature, T, 313, divided by our volume, 0.80 liters, okay? So, just running through that, our basic mathematics, division, multiplication, we come up with 4.5 atmospheres. How do we come up with those units? The moles cancel. Up here we have an inverse mole, a regular mole here. The liters cancel, numerator, denominator. The kelvins cancel, inverse Kelvin, Kelvin here. That leaves us with atmospheres. Pressure, we're looking for that, 4.5 atmospheres. But once again, you cannot go to your service station and say, I need my tire filled with 4.5 atmospheres. So as we said in the beginning of the equation, atmospheres times 14.7 equals PSI, okay? So we're just simply going to use the scientific method one more time. 4.5 atmospheres, which is in the numerator, over 1, which would be the denominator, over 14.7 PSI, which the numerator, and then the denominator 1 atmosphere. Atmospheres cancel, leaving us with PSI, 4.5 times 14.7, 66 PSI. So, going back to the original question, calculate the pressure developed in an 800 mil bicycle tire. We now have that pressure, given all these parameters. And the PV equals nRT is in a closed system, okay, as it's been specified if you research some of that. So, we have 66 PSI as our answer. So, very useful equation in figuring out parameters in a closed system of either pressure, volume, quantity of a particular material, or temperature. And using those units within the specialty gas constant, there are other units you can use too. For example, pressure can be used in torque, can be used in kilopascals, but we're not going to get into the other different units and specialty gas constants which would be associated with it. But for the purpose of this lesson and for this particular sample, now in a real world application, we've come up with an answer of 66 PSI for this question. So, getting back to the original assignments and thoughts we want to take from this lesson, we want to think about adiabatic cooling, which in the real world which is reducing heat through a change in air pressure. Where do you think that might exist in the real world, in nature? As weather, for example, goes up a hillside or a mountain and climbs down, the temperature changes and the pressure changes, and there is a direct relationship associated with that. And in meteorological terms, that's called orographic lifting. And when your homework assignment, in this particular case, will be to give me an example of perhaps a mountain chain where orographic lifting occurs. Could be locally, could be anywhere. And talk about that. Research the term orographic lifting itself, okay? And give me a short paragraph on that, or just a couple sentences. Next thing, we want to talk about, become familiar with, are ambient conditions. Think about your surrounding conditions. We talked about temperature a little bit. Ambient temperature 68 to 75. What I'd like you to think about, and maybe just give me a couple quick examples, are what you consider to be ambient conditions other than temperature. You might want to think about ambient pressure. And remember, very important to include your units in this. An ambient humidity. Pressure atmospherically can be measured in millibars. It can be measured in, not coming to me right now, but if you do a quick search on the internet, pounds per square inch, of course, as the tire example we just gave. And then finally, what I want you to do is give me 3 other examples of a diatomic molecule. We talked about nitrogen. We talked about oxygen. There are actually 6 other diatomic molecules that exist on the periodic table, and I'd like you to do a search on diatomic molecules and at least give me an example of 3 other examples of diatomic molecules. So that's my lesson for this particular occasion. I know we went over a lot of information, and since I don't have a class in front of me, it was mostly teacher talking and interacting with my assistant here a little bit, but she's not a science person. She's a criminal justice person, so college level. And Ashley, thank you very much for helping me out here, and I think that is going to close us out. Now the next issue will be for me to get this onto YouTube, which I'm not familiar with, which of course I hope you can help me. Okay?
Absolutely, sir.
Okay. All right. Thank you one. Thank you all.
All right.